Okay, so before we get started, there's an important thing that I need to make sure everybody understands. The DSA Lab Access. So basically from this week onwards, okay, this week onwards, that means, next week onwards, all right, you can go to the lab, okay, to work on your project, okay, on all your studio days, on studio time slots. That means Tuesday and Thursday. All right, so Tuesday and Thursday, 2 to 5 p.m. Okay. If you want to go on other time slots, okay, the main issue right now is because of your sort of lab uh, student size limit. All right, it's a bit difficult to accommodate. Okay, so please stick with your timing. All right, if you want to go, let's say you want to go a bit earlier. All right, so from 2 p.m. instead of 2 p.m. you want to come earlier, 1 p.m. whatever, that may be possible. All right, what I will do is I will let you know which are the days I can come in earlier. Okay, so those days I'll come in earlier and I'll open up the lab for you all. Okay, so that you all have a bit more time to use the lab. Okay, but other than that, do not go in other time slot because your other students, your other batchmates will be there. All right, they'll be using it. All right, and we need to be mindful of the safe distancing and the limit that we have in terms of number of students. Okay, so stick with your timing. Okay, and I think it's also next Tuesday. Okay, next Tuesday is actually an online. It's our last studio. Okay, it's our last studio, but it's an online one. Correct. Okay. So what I can suggest to you is this. Okay, in order not to waste the time that we have, you all can choose. Okay, those who are free, you can choose to come to the DSA lab and do your studio there. Okay, if you have already done your work, everything is done, you can just log into the Zoom, discuss with your TA, show that you have done everything, and then you can spend the rest of the time to work on the project in the lab itself. Okay, so this is a suggestion I can give you so that you do not waste the next Tuesday slot. All right, you can start to work on your studio, get everything done, get your data, whatever. Okay, but you still log into the Zoom first, and then after the briefing, when I send you all to the breakout room, if you've already done everything, you can just tell the TA that you have done everything. Show them, show the TA that you have got your results, everything is there. Then you can log off and you can just go ahead and start to work on the mini project. All right, so that is something that you can do next Tuesday itself. All right, rightfully next Thursday is the day where it's free. All right, but next Tuesday itself, you can still make use of that time slot to work on your project. All right, so that is a suggestion I can give you. Okay, so other than that, please stick with your timing. All right, so that we do not get into any issues with the lab. Okay, so let me go through with a quick review first. So the first thing that we did was on the IR proximity sensor. Okay, and then we basically built up the circuit, and what we saw is we measured the voltage coming out. Okay, based on the distance. All right, and now we saw that for most of us, okay, for most of y'all, around 2 cm, okay, to around 6 or 8 cm, okay, is where you can see there is some sort of a sort of linear relationship. Okay, so of course it sort of tapers off and things like that. All right, but we saw that the greatest change in the output was somewhere between 2 cm to 6 cm. Okay, so this is of course specific to this particular IR sensor model that we've given you. Okay, if you change to a different type of IR sensor, then definitely the behavior is expected to be different. Okay, so every hardware you buy or you use, we need to understand how it behaves, how we need to connect the circuit, and then we take measurements, and then we know how to use it. All right. Generally, in most cases, many of these components will have the data sheets, which will also give you this kind of graph. Okay, so in most cases, they will have some information regarding what kind of voltage reading to expect, what is the operating mode of the device, and so on. So all of this information would be available in the datasheet of the component. Okay, so this IR proximity sensor circuit that you built is important. Why? Because if you look at your M boards that I passed around yesterday, you can see that you need to fix IR sensors on both the sides of your M board. All right, so you need to make sure that they are positioned properly and you place them in the center of the grid space. Okay, and then based on that, you should be able to do a measurement. Okay, to know roughly what kind of voltages you expect. Okay, in order to be able to get the correct reading to stay within the center of the grid. Okay, so the moment your voltage starts to sway, okay, then you know you're going too close to one side. Correct. So that will give you an indication that you need to readjust your motor alignment. Okay, so the proximity sensor is important, correct, because your robot has to go straight, okay, as much as possible. So you need to make sure that when you build the circuit, okay, you get your readings, you do your calibration correctly, okay, and all of that is done properly in your code. Okay, another important thing you would also notice is that the wiring has to be very neat and tidy. Okay, do not have wires protruding out of your M board like that. Okay, or like that. Okay, why? Because all of these can be easily get tangled up or can get disconnected. Okay, and also can easily get stuck. Okay, so if you notice the grid space when we put it up. Okay, so next week we should be removing the top of the table and putting up the grid space. So the grid space actually has all these connectors. Okay, so you can see all these connectors over here. All right, and between these connectors we will place the maze wall. Okay, so we need to make sure that we do not bang into the wall and we do not get stuck inside these connectors as well. Okay, so it's important that you do not have any wires or anything loosely hanging out of the robot in any way. Everything should be very tightly wrapped around the robot. Okay, so that is those are some of the things you need to do. So if you see down here, okay, they have used scotch tape over here. All right, so you can use scotch tape, you can use blue tack, okay, you can use whatever you need to use to make sure that everything is secure and is tight, okay, on your M board. Okay, and over here, this is the line, the sensor to detect the black line. So that is already given to you, okay, those IR sensors. So you just connect it up and that will give you the, or that will help us to detect the black strip on the floor of the maze. All right. Okay, so we can discuss more on that later on. In terms of the RGB LED LDR, okay, so I explained this again in the studio. So you just need to make sure you remove the top translucent cover, okay, and you see that the two RGB LEDs and LDRs are exposed. All right, and one thing that I also shared with you is most students in the past built up a sort of a square black box around it. Okay, so again, that was the intention of that was to make sure that the light is sort of concentrated upwards. All right, and so that gives you a more consistent reading of the LDR values. Okay, so you can also try that. Okay, or you can choose not to do it. So all these things are optional. Correct. So if you think you want to add that black box to sort of channel the LED light, you can try, okay, and see where that helps you with getting a more stable response for the LDR. Okay, so after talking about sensors, we moved on to the part on signals and sampling. Okay, so we saw that there are basically two different types of signals. In reality, everything in the world is continuous, correct? It's always continuous, but a continuous signal is always difficult to capture and measure, correct? So in order to capture it and do some measurements, considering that everything is moving towards using software and using microcontrollers and so on, we want to be able to digitize them. All right, so to digitize, we need to take sample values, okay, discrete values of the continuous analog signal. Okay, so that is where the sampling concept comes in. So by sampling, basically what we're doing is we are saying that we have a signal that is always changing, all right, but we want to store this digitally And to store this digitally, we take samples of the signal at some specific sampling interval or at a specific rate. Okay, and the whole idea is, by looking back at the samples, I must be able to reconstruct the original signal as closely as possible. Okay, so of course there's always a chance that some information might be lost. All right, so that is something that we accept. Whenever we move from analog to digital and digital back to analog, there will be some information that is lost, because whatever is in between, we are just extrapolating. Okay, so but that is something that we accept. All right, because we still want to go ahead with moving everything to digital, and then finally we can move it back. Okay, so of course the more samples we get, the closer it is. Right, so if instead of this I sample even at double this rate, so I can capture more signal in between. Correct, so if I double this, I can capture more signal in between. So the more I capture, the more accurate I can reconstruct. All right, but the more I capture means two things. I need a lot more memory space, okay, to store this data. And if I want to process this data, I will also need more processing power. Okay, so it's always a trade-off. Right, when you're building systems, it's always a trade-off between how much data I want to deal with compared to how good I want to be able to reconstruct the signal. Okay, so it's always a trade-off. Okay, so the minimum sampling rate is always or is given by this sampling theorem, that it must be greater than or equal to 2 times the maximum frequency component in the signal. Okay, so we say maximum frequency component in the signal because a signal can have different frequency components. Correct. So the best example is our voice. Correct. So when we talk, we have a particular frequency range. All right, so in general, do you know what is the frequency of speech? Anybody? Anybody will take a guess? What is the frequency range of most of our speech? Okay, so it is around, okay, it's around maybe 20-30 hertz. Okay, okay, so the lowest frequency of course is maybe 20 or 30 hertz. Okay, but the highest, okay, when we talk normally, it is estimated, okay, to be around 3.4 kilohertz. Okay, so this is the normal human voice range. All right, so that is why, okay, telephone systems, okay, mobile phone systems, we sample at 8 kilohertz. Okay, we sample 8 kilohertz. So we round up to 4 and we sample at 8 kilohertz. That is why, okay, whenever you talk on the phone, okay, you can hear the other person clearly because we are oversampling by a little bit and we can reconstruct everything clearly. Okay, so if you were to sample lower, you will not be able to get back the original signal. Okay, so of course, if you sample higher, the voice is more clearer, correct? More sharper. Okay, but of course that adds a lot of overhead to the entire mobile network, correct? In terms of how much data to transfer. Okay, so 8 kilohertz is ideal. Okay, so we just exceed the minimum sampling frequency by a bit, and it's enough to reconstruct it well enough for us to hear. Okay, so that is a example of what we mean by the maximum frequency. So we always try to look at the maximum frequency. So it also makes you understand why if you try to play a song to your friend over the phone, it doesn't sound the same at all, right? Because your song is having a much larger frequency range. Okay, so when you try to play a song over the phone, the other person is hearing a signal that has not been sampled at the sampling rate. Okay, so there's a lot of aliasing taking place. So a lot of signals, a lot of information is lost, okay, over at the receiver side. Okay, so these are the basic concept of Nyquist rate and Nyquist frequency. All right, so the Nyquist rate is the minimum, or 2 by f is the Nyquist rate, and the Nyquist frequency is fs by 2. So just make sure that you remember these terms correctly. What is Nyquist rate? What is Nyquist frequency? So just remember these terms. Okay, so these are some of the things that can trip you up in the next final assessment. Correct? So there can be a question and then they're asking you for Nyquist rate, but you thought it's Nyquist frequency or the other way around. Correct? So just make sure that you clearly know what is Nyquist rate and what is Nyquist frequency. So the terminology, just be clear of that. Okay, so in the case where you are sampling lower than the Nyquist rate, okay, what you get is you still get data points, all right, but when you try to reconstruct it, okay, you will get a signal that is very much different from the original signal. Okay, so that is called aliasing. Okay, so we just have this understanding first, right? All the mathematical analysis behind it, all of those you will study in other modules. All right, okay, when you study about communication, you're talking about signal theory and so on, then you will study all the other details about this. But for now, we just take it that if I do not fulfill this sampling frequency of a double of Fmax, what I will get is aliasing, which means that I will get some other signal that is not representing the original signal. Okay. Okay, so those were the concepts that we covered in class. Okay, so let me switch over first to this. Okay, so let's go through the tutorial questions. Okay, y'all can see the screen. Okay, good, thank you. Okay, so let's go through the questions. So the first question is asking us to design a bandpass filter for the 4th octave of musical notes. Okay, so don't worry about that. What we're interested in is the actual frequency range, correct? So we're interested in designing a system that goes from 261 to 493. Okay, so if I were to draw the response of the filter, okay, it's going to look something like this. Okay, where we have the 2 cutoff. Okay, 2, 6, 1 and 4, 9, 3. Okay, so the important thing that we must understand is this is the high pass filter cutoff. Correct, so this is the FC of the high pass filter and this is the FC of the low pass filter. All right, so these are two things that you must understand. So the high pass filter cutoff is 261 Hertz and the low pass filter cutoff is 493 Hertz. All right, now for the filter, again, we have only covered the first order filter in EPP1, second order, third order, and so on, you will cover in other modules. All right, so for first order filter, the formula is the same, whether it's high pass or low pass, correct? Because it's the same RC. Only thing is which way you connect it. All right, so if you look at the high pass filter, okay, the high pass filter, we say that the FC is equals to 261 and FC is 1 over 2 pi RC, correct? So in this case, I call it H and H. So the high pass filter RC is equals to 261. Okay, so when I try to, so if I solve it to get the R and C combination, I'll get it as 609.79 microsecond. Okay, now what is the next step? Okay, so the next step is when you're designing a filter, all right, on your own, you need to make some decisions, correct, some choices. So I know that the RC value together must be 609.79. All right, so the decision you can make is I can choose one of the components first, then I solve for the other. Because the question never gives us any specific restriction, correct? They never say use this particular resistor value or this particular capacitor value. So since they did not give us that restriction, okay, in a real world scenario, you will choose one of the components and then find the other. So what should I choose? Should I choose the R or should I choose the C? What do you think? Okay. Okay, so some say R, some say C. Okay, so it comes back to what is easier to sort of vary to the exact value that I want. Okay, Take for example, if I fix R at 10K, okay, let's just say I fix R at 10K, then I get my capacitance as 109 microfarad. Okay, you cannot get a 109 microfarad, correct? Or you may find it very difficult to find a 109 microfarad. So the capacitor value, if you remember what we have used so far, they are all very fixed values, correct? And of course, is there a variable capacitor? There is, okay, but it is a very expensive piece of equipment to have, okay, variable capacitor. Whereas if I fix my C, I can get any value of R using a potentiometer, a variable resistor. And a variable resistor is a lot cheaper than a variable capacitor. Okay, so in terms of economical sense, all right, practically, yes, you can argue either way, it's fine. Okay, but practically, if you, let's say you are going to build this filter on your own, the best choice would always be to fix the C first, because the C is a standard component you can just take off the rack. All right, for the R, even if I get some funny value, 605.2 kilo ohms, no problem. I can use a potentiometer and still tune until I can get it. All right, so it is always easier to fix the C first, and then you choose the calculate the R, and then you can use a potentiometer. You can use some combination of resistors to get it. It's fine. Okay, so you can choose any C. All right, so this question is a bit open-ended. All right, so your answer can be very different from what I'm going to show you. As long as you follow the process, it is fine. Okay, the process is the important thing that you're focusing on. Okay, your answer and my answer can be very different in terms of RC values. Okay, so the example that I'm going to show you is just a choice. Okay, there's no particular reason for this choice. Okay, you could have chosen 1 microfarad, 20 picofarad, doesn't matter. Okay, so there is no particular reason. You could have chosen any capacitance value and you just get the appropriate R value. Okay, so if I choose C as, let's say, 20 nanofarad, okay, that will give me my R as 30.5 kilo ohm. Okay, so again, I repeat, this is no particular reason why I chose this C. It is just a choice. You could have chosen any other nanofarad or picofarad or microfarad that you can get off the shelf. Okay, so whatever capacitance value you have chosen, you just calculate the corresponding resistance value. Okay, so we know that for this sort of high pass filter, the circuit is going to look like this. Okay, where this is your CH and this is your RH. Okay, so that is the high pass filter part. Okay, now we just have to repeat the same thing for the low pass filter. So for the low pass filter, again the FC is equals to 493, which means 1 over 2 pi RL and CL equals to 493. So RL CL is going to be 322.83 microsecond. So the same thing as before, you can choose any C value. All right, but this is the thing you need to be careful. If you remember the last studio or the last tutorial, we talked about the loading effect. Okay, so if you look at the whole filter design, okay, if you look at the whole filter design, okay, there is a capacitor and a resistor, and then that is the high pass filter part. Okay, and then we say that we connect to another resistor and capacitor. Okay, and this is the low pass filter. Okay, so in the last tutorial, we talked about the loading effect. Okay, so this is the R for the H, and this is the R for the L. Okay, so in order for us to minimize the loading effect, okay, what we said is RH, okay, or RL must be a lot bigger than RH. Okay, because this is considered two parallel branches. Okay, so look back at the previous tutorial that we discussed. So if you remember, this is the point, okay, and we wanted this voltage at this point here to not be affected by this branch. Okay, so in order for the voltage at this point to be not be affected, okay, when you have two parallel resistances over here and here, the combined resistance will be the one that is closer to the smaller one, correct? So when RL is much bigger than RH, then the effect of this branch here, the RL and C will be much will not impact the overall impedance that you see at this point. Okay, so that was the loading effect that we discussed last. All right, so taking that into account, all right, we want the RL here to be a lot higher. So if you want the RL to be a lot higher, okay, so this RL should be a lot higher than your RH. Okay, so since they are both multiplied by each other, all right, what I need to do is I can make the CL lower. So by making the CL lower, the RL can become higher. Okay, the RL can become higher. So what I can do is I can choose a CL that is, for example, 1 nanofarad. Okay, you can go lower also, no problem. All right, and by doing that, I can get a RL of 323 kilo ohm. Okay, so you can see that your RL here, your low pass filter resistor, is 10 times more than your RH. All right, so you satisfy this condition that your RL must be a lot bigger than your RH, so the loading effect will not be seen. Okay, the loading effect will not be seen. Okay, so your low pass filter design is basically your resistor first, followed by capacitor. So this is your RL, and this is your CL. Okay, so when you combine everything together, this is your overall band pass filter. Correct. So let me put in the values. Okay, so the values that you get here are 20 nanofarad here, 30.5 kilo ohm, and this is 323 kilo ohm, and this is 1 nanofarad. Okay, so rightfully this is already your high pass filter output. Okay, but as what we have seen in the lab, all right, it is always good to connect it with the op amp, so that when you attenuate what you do not want, at the same time you are amplifying what you want. Okay, so the whole idea of filtering is you remove what you do not want, but at the same time you also have the idea of amplifying what you want. Okay, the reason why you amplify it is because when your signal becomes bigger, okay, it uses a bigger range of voltages, which means that when I do sampling later on, it will actually help me get a bigger range of values. Okay, so what we can do is we can connect this to op amp. Okay, and again, you can use any op amp configuration since nothing is clearly specified in the question. So if I were to choose a non-inverting configuration, okay, so again, there is no particular reason for this. It is just a random choice. Okay, you could have chosen anything. Okay, but of course, okay, wait, coming back here, this is a music, right, musical note. So for musical notes, okay, since it is an audio signal, it is better to use a non-inverting configuration. Okay, so this is the output here, and your filter, sorry, your feedback resistors can be here. So you can use any values that you want. Okay, so if I put a value of 10K and 1K, so it become a gain of 11. Okay, so okay, so okay, let me look at the questions first. Okay, so filtering will not be perfect in a sense that, okay, we will definitely not get the exact cutoff. So in this case, we are trying to design based on the exact frequencies given to us. Okay. In reality, of course, we know that this will not be the exact band cutoff frequency we get, correct? Because, for example, over here, even though we say that there is, we minimize the loading effect, there is still some loading effect, correct? But it's just very small. So effectively, we will not get exactly the cutoff frequencies that we say here, okay? But again, this is just to understand the idea behind how to design the filter. Okay, in general, when you're designing a filter, you will usually include some buffer. Okay, that means if this is the signal range that I want, 261, okay, to 493, okay, I will not design a filter to be so exact. Okay, unless I am designing a second order or third order filter, then maybe it is still okay. Okay, you can get a very close cutoff. Okay, but in general, you will want to have some buffer if possible. That means you may want to bring this down a bit and bring this up a bit. Okay, again, there are many ways of thinking about how you want to design the filter. All right, it's a matter of what any specific requirements you have. Okay, so if you look at last tutorial question, for example, there was a specific requirement that there is a noise at 10 kilohertz and I want to reduce the noise by 20 dB. So that is a very specific requirement. Okay, so that specific requirement, then you build to fulfill that requirement. Okay, so in this case, there is again no specific requirement. So we're just dealing with the frequencies that we have. Okay, another question is, does it always have to be high pass and low pass? Okay, not necessary. Okay, you can swap low pass and high pass first. Okay, but either way, it is fine. All right, both ways it is fine. Okay, the amplification, like I mentioned, is you want to amplify the output signal. All right, because you have a signal that has a particular frequency range. Okay, so for example, okay, so let's say this is my signal. Okay, and then maybe, okay, let's say this is my audio signal. Okay, let's assume this. All right, so of course, maybe there is some high frequency noise at certain parts. Okay, and you do filtering. Okay, so after I filter, okay, so let's say I do filter, and after I do the filtering, okay, I get a filtered signal, and let's say the filter signal looks like this. Okay, so by filtering, I remove the noise. Correct, but then you can see that again, these are things that there are more steps involved. Okay, if let's say now this signal, okay, let's say this is a audio signal, okay, but it's a very soft audio signal, and let's just assume that this voltage here is around 3.1 volt. Okay, so the gain of 11 here is, this is a non-inverting amplifier, correct? So 1 plus RF over R1, 10 over 1. So that's how we get 11. Okay, so let's look at this example here. So let's assume this is my audio signal. All right, it's a soft audio signal and it's around 3.1 volt, for example. Okay, now if I were to zoom in, okay, let's just say I zoom in here. Okay, let's say I zoom in. Okay, so let's say I magnify this. So let's say this is 3.1. Okay, and then let's say this is 2.5 and this is 3.6. So I just zoom into the within the range here. So if I just zoom in, it looks something like this. Okay, now if I were to take this signal, okay, so what I'm telling you now is beyond the scope of what you need to know, but I just telling you why we need to do it. Okay, so it's not part of the syllabus, all right, but it's something that you will have to deal with later on, okay, in other modules. Okay, so if I have this signal, okay, and I try to do a to D operation, let's say I want to do a sampling. Okay, if I do a sampling of this signal, okay, that means I take samples at all these points here. Okay, what you will see is most of the sample values will be almost the same. Okay, why? Because this range here is too small. Okay, it's too small. So this again relates to the way the ADC operates, the resolution and all these things. So again, this is beyond what you need to know. All right, but I'm just telling you, when the signal itself is very, very small, that means it occupies a very small change in the magnitude. If I try to do a sampling of the signal, what will happen is all these values will be almost the same, maybe 1 or 2 bit only difference. Okay, so you are not able to capture what is really happening. Okay, but if I magnify, okay, I magnify this signal, okay, through op-amp, and then I'm able to sort of boost the signal. Okay, so the same thing, okay, but 3.1, but now maybe I can bring it up to 5 volts, okay, and up to 1 volt maybe. Okay, so +2, -2, and the signal now looks something like this. The same signal, but just boosted up. Now my signal occupies a bigger range. All right, a bigger range. So when I do sampling, I'm actually able to get the actual changes in the voltage in the samples values that I'm going to look at. Okay, so that is why we always want to look at whether or look at amplifying the signal. Okay, it is not necessary, okay, all the time. Okay, in some cases your signal is already loud enough, okay, or already amplified, and you just want to remove the noise. Okay, so that may not be necessary. Okay, so again, I'm not going to go into all the details and talk about this too much. Okay, so I'm just going to give you this idea only on. Okay, but again, the amplification is necessary, okay, in cases where you feel that the signal is too small, okay, and you want to boost the signal to process it later on. Okay, but theoretically, yes, the filter portion, which is this is the part that actually does the filtering. Okay, the amplification is an add-on, okay, where you want to boost the signal after you filter so that the subsequent processing stages have a better quality signal. Okay, so that is the idea. Okay, so that is question 1. Okay, so whether we amplify or not, again, it is not say every time, correct? So we need to look at the question. Okay, so if the question say we need to amplify, then we look at amplification. All right, if it is not specific, then it is an optional thing. All right, so then we just focus on the filtering part. Okay, so all depends on what is the question asking. Okay, what are they asking us to find, or what are they asking us to analyze? Okay, so now let's look at the next question, the LM35. Okay, so the LM35 is a commonly used temperature sensor IC chip. Okay, and it can be powered by 4 to 30 volt power supply and the output. Okay, so the first thing that you all should do is what? Is to actually go and check on the data sheet. So I don't know whether any of you downloaded the LM35 data sheet. Okay, so if you just go on Google LM35 temperature sensor data sheet, okay, you'll get this. Okay, and like I said, always try to make it a good point, a good habit to get the data sheet of whatever hardware you're dealing with. Okay, so that gives you a lot of important information on how it works, how to use it, and so on. Okay, so over here they've given you all the details of the temperature sensor, and of course one of the important things you want to know is how do I connect it up. Okay, the pinout. So if you look down here, the LM35 basically has 3 pins. Pin 1 is your VCC, pin 2 is your ground, and pin 3 is your Vout. Okay, at the same time, you also have this LM35 in a IC package as well, so something like your op-amp or your 555 timer. Okay, so they also have it in an IC chip format. So all these are things that is good to know, correct? Because when you're building your own project, okay, or something you're working on, okay, you want to know how the sensor operates, okay, and at the same time, you also want to know what kind of packaging options are available for me, all right, so that I can decide how I want to use or which variation I want to use in my project. Okay, so that is basically the LM35. So your LM35 sensor, as what we saw from the data sheet, okay, is a 3-pin device. Okay, the first one here is going to your plus VCC. Your second one is going to ground, and your third pin here is your actual temperature reading. All right, so if you buy this chip or you're given this chip, at least now you know how to use it. All right, and we are also given some information that it is 10 millivolt per degree Celsius, and that it is at gives us a voltage reading of 250 millivolt at 25 degrees Celsius. Okay. So now the question is asking us to design a circuit. Okay. Let's give me a minute now. Okay, so it is asking us to design a circuit that will fulfill these two conditions here. Okay, where if my temperature, okay, is lesser than 35 degrees Celsius, I will on a green LED. Okay, and the temperature is greater than 35 degrees Celsius, I will on the red LED. Okay, so how will I design this? Okay, so the first thing we must see is that the input signal itself is very small. It's millivolt range, right? It's millivolt range. Okay, so what we would want to do is always amplify the signal. So this is what I mentioned just now, correct? The sensor is giving us signals, all right, but the change in the signal is very small. All right, so even though my temperature can be changing, it is still very small. So if you imagine that at 250 millivolt and 25 degrees Celsius, and I'm changing 10 millivolt per degree Celsius. All right, so if I go up by 10 degrees to 35 degrees Celsius, so this one will go up by 100 millivolt. So it'll be 350 millivolt. Okay, at 35 degrees Celsius. Okay, 250 millivolt to 100 to 350 millivolt, only 100 millivolt difference. If I try to do a to D operation on this, again, I will not be able to differentiate between both of them. Okay, they are too close to each other. Okay, they are too close to each other. So this is the example of where I need to do amplification in order to get a better range of the signal. Okay, so how much amplification I need? Again, the question never specifically give us any constraints to follow. Okay, so I'm just going to give you one approach to solving this. All right, you can have different ideas, okay, but as long as the approach is the same, then it's fine. Okay, so the first thing, okay, since the signal change is very small, okay, very small, only 100 millivolt from 25 to 35, that means it's only 10 millivolt every degree Celsius, we need to amplify the signal. So the first thing is, okay, I'm going to take this signal, okay, and I'm going to amplify it. Okay, so to amplify it, I can pass it through an op-amp, okay, and you can use, wait, okay, so you can use any resistor pair combination. Okay, it all depends on what gain you want. Okay, so what I'm going to do is I'm going to connect it up this way. Okay, and I'm going to use 9K and 1K. Why? Because 1 plus 9 over 1 will give me 10. All right, so what I'm going to get here is 350 millivolt. Okay, and I multiply by 10, so what I get here is 3.5 volt. Okay, you could have chosen any combination, then you get some other voltage, that is fine. All right, so again, this is just one way of solving it. You can design it your own way as long as you fulfill the requirement. The requirement is when my temperature sensor hits 350 millivolt, I must be able to differentiate by turning on or off the LEDs. Okay, so by multiplying by 10 from 350 millivolt, it becomes 3.5 volt. Okay, now to do this, okay, to do this part over here, we basically know that we need to use a comparator. Okay, we know we need to use a comparator. Okay, so we have seen this in our earlier studios. Okay, so to do this, okay, let's do the first one first. Okay, so let's I want to compare this, okay, to be to the point where it is bigger than 3.5 volts. Okay, so this signal here, I'm going to connect it to the positive of the op amp, and the negative of the op amp, I'm going to connect it to a reference voltage. Okay, and since I'm comparing for 3.5 volts, so of course this is not always 3.5 volts, it will fluctuate. So at some point it can go higher, at some point it can go lower. Correct, so it can go up to 4.2 volts. Okay, it can go down to 2.7 volts. We do not know. All right, it's always fluctuating. All right, but this op amp, I want it to compare to know when it goes. Okay, so let me call this point here. Okay, let me call this point here VT. So this op amp, I want it to such that when VT is bigger than 3.5 volt. Okay, so the negative is the reference voltage. Okay, so the reference voltage must be 3.5, all right? Because when V plus is bigger than V minus, my output will go to plus V set. Okay, when V plus is bigger than V minus, my V out will be plus V set. All right, so what I need to do is, in this case, I'm comparing with 3.5 volts, so the V minus must be tied to 3.5 volt. Okay, so how do I get 3.5 volts? You can do it whichever way you like. Correct. Okay, so the easiest way is, okay, I'm just assuming a simple way out. Okay, I'm just going to connect two resistors. Okay, 1K, 1K, and I'm going to say that I have a 7 volt source. All right, so I'm just taking the easy way out. If you say you have a 5 volt source, then you choose two resistors such that you get 3.5 volts, okay, by voltage divider. Okay, in this case, I'm just taking the easy way out. I say I got a 7 volt source. So 1K, 1K means the voltage at the center here would be 3.5 volts. Okay, so when my voltage at the V plus terminal is bigger than 3.5 volts, the output over here will be plus V set. That means it's positive, all right? So it could be 5 volts, it could be 10 volts, doesn't matter. So if it's positive, I want it to drive the red LED. Okay, so the red LED is going to be connected here. Okay, and of course I need to connect a resistor, go to ground. Okay, so this LED, this red LED here, will light up. Okay, whenever my V plus is bigger than V minus. Okay, and V minus is your reference, which is 3.5 volt. Okay, so that is the first part of the circuit. The second part of the circuit is exactly the same. Only thing is, now you have a plus and minus. And in this case, what you want to check here is when VT is lesser than 3.5 volt. Okay, so when VT is lesser than 3.5 volt means you need to connect it the other way round. Okay, that means the signal is now connected, okay, to the negative of the op-amp, and the reference is connected to the positive. Okay, so if you look at it the other way around, basically you are trying to check for the situation where 3.5 volt is greater than VT. So this is connected to your V plus, and this is connected to your V minus. Okay, so when this condition is fulfilled, then this op-amp will be saturated, the output is high. Then I can say I switch on the green LED. Okay, and then I go to resistor and I go to ground. Okay, so the resistor value depends on several factors, correct? Again, there is no information or guideline on what is the power supply to the op-amp, correct? So if it's plus minus 5 volt means this, then you say this is 5 volt, correct? So if this is 5 volt, then you can choose a resistor that matches the current limit of the LED. Okay, so it is all depends on what LED or what is the characteristic of the LED. Okay, what is the current limiting resistor you should use? Okay, so of course many times you will use maybe 560 ohm, sometimes they use 180 ohm. Okay, so it all depends on that. Okay, so the LED itself, if you just connect it, okay, it will still light up, all right, but there's a high chance it will blow out very fast. Okay, because if the current is too high, okay, it will damage the LED. Okay, so you must always put a current limiting resistor to make sure you limit the current flow through the LED. Okay, so that will ensure that the LED can still remain functional. Okay, if not, it will work for a while, then after a while it will just burn out, okay, very fast. Okay, now of course this is okay, so this circuit here that you see basically solves the problem, right? Fulfill the requirement where we take the data from the temperature sensor, we are able to detect the temperature of 35 degrees Celsius, all right, because 35 degrees Celsius corresponds to 350 millivolt, all right, and your circuit will basically compare and use the op-amp to decide, okay, which LED should be on. Okay, so this is one way of doing the circuit. All right, so I'm going to show you another way of doing the circuit. Okay, where, okay, so let me demarcate this. So this is one way. Okay, the other way is, okay, so taking this signal over here. Okay, so instead of using two different op-amp, I'm going to, assuming that I tap directly from this point here, I'm going to use a single op-amp. Okay, so this negative here is your 3 point, this is 1K, 1K. So this is your 3.5 volt reference. Okay, so with a single op-amp, how can I still do this? All right, so let's look at it from the red LED part. So when VT, so this is your VT, which is your temperature of the module after it's amplified. So when your VT is bigger than 3.5 volt, so your V minus is your 3.5 volt reference. So when VT is bigger than V minus, you say the LED will light up. Okay, so this part we understand. So this LED will light up when VT is greater than 3.5. Now then, the second thing is, what should be the connection for the green LED? Okay, so for the green LED, basically what you need to do is you connect it in the reverse bias way. Okay, so by connecting it in the reverse bias, okay, so let me put this here. Okay, what is going to happen is when your VT is lesser than 3.5, then what will happen? When VT is lesser than 3.5, the signal here will be negative Vset okay, or 0, all right, depending on your power. So when your green LED is connected in the reverse bias way, that means your uh, anode is connected to the positive, then what will happen is current will now flow in this direction, which will light up the LED. Okay, when it is VT greater than 3.5, current will flow in this direction and light up the red LED. So at any point of time, only one current is flowing. Okay, so wait, let me. Yeah. So sorry. So for this to work, this should be negative V set, and this should be ground. Okay, so let me redraw this part here. Okay, so at any point of time, current will only flow through one way, correct? So it's either positive V set or negative V set. So if it's positive V set, current will flow in through the red LED and to ground over here. If it's negative V set, it will flow in the opposite direction towards negative V set, and it will light up here. All right. So at any point of time, only one current will flow. Current will flow through only one of the LEDs. The other LED will be considered to be reverse bias. Okay, so it won't flow. Okay, so this is another way of building the circuit. Okay, where your current, you use a single op amp to differentiate between two different current flows. Okay, so in this case, again, this works when your op amp is operating on dual supply. All right, so if you operate on dual supply, then your plus V set could be maybe plus 4 volts, and your negative V set could be negative 4 volts. So you will have current flow in both through both of these LEDs. Okay, depending on whether it's plus V set or negative V set at the output here. Okay, so if negative V set, if it's a single supply and negative V set is 0, then this configuration won't work. Okay, you will need to do something else. Okay, so this configuration sort of works with a dual supply over here. All right, so this is of course one solution, all right, where you use two different op amps for the comparator function. This is another sort of approach where you use a single op amp, okay, and you can still achieve the outcome. Okay, I mean, if you were to do something like this, okay, so in reality, if let's say you are going to do a project where you need to do something like this, okay, the best way would be to just take the signal and pass it to the A to D of your microcontroller, okay, and then do all the processing over at the software side. Okay, so that is always the easiest way, all right, because generally, okay, like I said, most systems nowadays are all moving towards the digital implementation or solution, all right, which means almost every device that has some processor, some microcontroller that can do this for us. Okay, so as much as possible, we just prepare the signal to give us a good signal to noise ratio. Okay, and then subsequently we do all the processing over at the software side. Okay, we do A to D conversion, take the digitized samples, and then we do all the processing later on in the controller. So in the controller, it's a lot easier for me to do all of this. Correct. In fact, this is the same idea you're going to use for your IR sensors, correct? Because IR sensors are giving you an analog voltage. correct? Okay, so if you were to build comparators and everything to try and compare this voltage, okay, to know whether you're closer to the wall or further away from the wall, is a lot of hardware, correct? So we are going to take the other way, which is take this analog voltage from the sensor and pass it through to the A to D of the Arduino, and then do all the processing in software. Okay, and then we can say that, okay, if my voltage that I get is beyond this certain threshold, means I'm too close to the wall or too further away from the other wall. Okay, and then I readjust. Okay, so this example is exactly like how your IR sensor is going to be. Only thing is, after we get the signal, okay, in our case, since our signal is already in a good range, correct, 2 to 4, 2 to 5 volts, all right, we no need to even do any amplification. We can straight away take the IR voltage and straight away use the A to D operation, and then from the signal we can make the decision of how close you are to the wall. Okay, so this is basically what you're going to be doing. Okay, so let's move on to the next question here. Okay, so for this next question, it's very straightforward. Basically, you're asked to look at are you going to sample 100 samples per second? So this basically means it's 100 hertz. Okay, so for each of the signals, whether we can reconstruct it. Okay, so basically what you need to know is, when I look at all these signals, it is basically sine or cosine 2 pi ft. Okay, so what is inside here is always 2 pi ft. So from there, we derive what is the f, and then we know what is the frequency. Okay, so if I look at the first one, okay, phi cos 500 pi t. So let's put it in frequency, your Nyquist rate, and your whether I can do reconstruction. Okay, so if my signal here is 200 pi, it means this is 2 pi, correct? That means my frequency is actually 250 hertz. So I need to sample at 500 hertz. Okay, so definitely there is not going to be any reconstruction here. Okay, so it doesn't matter whether it's a sine signal or cosine signal or anything. What we are interested in is the actual frequency only. Okay, so in this case, it is the frequency is 100. So I need to sample at 200. So again, the answer here is no. Okay, for this one, the frequency is 50, so I need to sample 100. Well, can I reconstruct? This is again, like I said, theoretically, yes. Okay, but the thing is, we do not need to, we can't really say, because if it's exactly, and you happen to be sampling it exactly at the same point again and again and again, you may end up interpreting it as a straight line. Okay, so it could be yes, it could be no, because it all depends on at which point you sample. Okay, so if you remember the example we saw in the studio, if I happen to sample at the top and bottom, then I can reconstruct a sine wave. But if I happen to sample exactly at the zero line, then you will just get a straight zero line. Okay, so it all depends. Okay, so again, we do not need to worry about sine wave or cosine wave. We don't need to do any conversion, because we are only interested in how fast I'm going to sample the signal. All right, so the other details, the amplitude, all of this doesn't matter. Okay, so in this 50 pi t, my frequency is 25, so I need to sample at 50, so I can definitely reconstruct. Okay, so in this question, we're just trying to emphasize the idea of looking at the frequency when it comes to sampling. Okay, so sampling will ensure again that by following a sampling rate, you should be able to reconstruct the signal. All right, so that is the whole idea of following this Nyquist theorem. Okay, so for the last question, we are asked to look at the condition for sampling period to correctly sample a signal given by this. Okay. Uh, so this is a classic example of a signal with multiple frequencies. Okay. So when you have multiple frequencies, okay, so what you get will be a mixed wave. Okay. So maybe if you look at your time waveform, okay, you will probably get a signal that has sorry, not, so you may get a signal that looks like this. Okay, so it all depends on how they are sort of superimposed together, so you will see multiple waves with different frequencies all sort of combined together. Okay. And what we want to know is, in order for me to fulfill the sampling theory, I need to, or the sampling period, I need to make sure I look at the highest frequency. So in this case, the highest frequency is this. All right. So in this case, the frequency is 10 hertz. Sorry, the frequency is 5. Okay, because this is 2 pi, which means your sampling frequency must be greater than equals to 10 hertz. All right, because this is the highest component, highest frequency component in the signal. Okay, so since the highest frequency component in the signal is at 5 hertz, I need to sample at 10 hertz. So the sampling period must be lesser than equal to 0.1 second. Okay, so you do not need to worry about changing sine to cosine or doing anything other than just looking at the sampling frequency when you want to know whether the signal can be reconstructed, okay, or what frequency I need to sample on. Okay, so whether it's sine, whether it's cosine, all doesn't matter. Okay, we only need to worry about the actual highest frequency component in the signal. Okay, so the question 4 is quite straightforward. We just need to focus on the highest frequency component. Okay, so again, this is just focusing on the sampling concept only. All right, to get a good range of values, all right, that is the A to D conversion part. All right, so that part is what I mentioned over here, what we want to amplify. All right, so that is the first question over here. Okay, so over here, okay, in order for me to get a good signal, okay, or to make good use of the signal, I want to be able to sample at the correct rate, but at the same time I want the samples to clearly represent the actual signal as much as possible. Okay, so if your samples are all too close to each other, you will not be able to differentiate. Okay, so that is why we are doing the amplification before we do sampling. Okay, so that is the other part. All right, so as you can see, it is not one theory at one time. It's a few things together. We need to look at it. All right, so we need to look at, for example, in this question, we need to look at the sensor itself, how it behaves, how it operates. All right, and then from there we look at what kind of gain I need to provide. Okay, and then after I provide the gain, what is the next step? Okay, I can build further analog circuits to do some decoding, or I can move it to the digital platform by doing an A to D operation. Okay, so these are all different options, okay, for us to explore. Okay, so this tutorial gives us like a good overview of some of these things, all right, to look at it from different aspects. Okay, the component wise, the analog side. Now we're moving to the digital side. Okay, so basically that wraps up the tutorial for today. So yeah, I think that's all I have. Okay, so as I mentioned just now, okay, for the DSA lab, you can start coming to the lab on Tuesday itself. All right, you can do the studio at home, okay, but when you come to the lab, you can just log in first. All right, and then once your TA verifies what you have done everything, you can log off and you can just start working on your mini project. All right, and then subsequently you can stick to the timings. All right, as and when I can come to the lab earlier, I'll let you all know, so you all have some extra time to make use of in the DSA lab. Okay, so that's all I have. Okay, thank you. Bye.